finished the last session talking about digital signatures. Now, we talked basically about two different things until this point. Can you hear me at the back? Is everything fine? Okay. So we talked about two things until this point. The first one was encryption, how you can send messages that no one else can read, basically. And then the second thing we talked about were digital signatures. And the idea here was how to send messages that no one else can tamper with, so that if they changed your message, the recipient knows that this message was not really from you. And we had basically two different types of bad guys here. We had Eve, who wanted to figure out what our message is. And we had Charlie, who wanted to change our message. So my general setting is that I have Alice and Bob. As usual, they want to communicate with each other. But now let's say that the adversary might do both of these things. So the adversary wants to figure out what the messages are, and it might also change my messages. So I want to defend against both of these. And we talked about this towards the end of the last session. We said that basically, if Alice wants to send a message to Bob, she first signs the message and then takes the message and the signature and encrypts the entire thing and sends it to Bob. But I just want to be a little bit more specific about how this works. So Alice has a private key and a public key. So let's say I call it D1 and E1. And let's say that D1 is Alice's private key for receiving encrypted messages. So this is for decryption. E1 is the public key that Alice sends to everyone else, and everyone knows that if they want to send a message to Alice, they have to use E1. So these are the keys for encryption. But then she has a separate set of signature keys. And the signature keys are basically, let's say, D2 and E2. And these are different, and actually, they might even have a different modulus when we're talking about RSA. So I have like an N1 here and an N2 here. But I don't want to put too much emphasis on the modulus, so I don't write it, but you know that all the calculations are modulo some number N because we're using RSA. And then Bob has a similar situation. So he has two pairs of keys. One pair is used for encryption, and one pair is used for signatures. So let's call this D3 and E3 for encryption. And let's say that the ones here are D4 and E4. Okay. So now let's say that Alice wants to send a message M to Bob. What does she do? Well, she wants to send M. So Alice wants to send M to Bob. Well, the first step is that she has to sign the message, because when Bob receives it, Bob has to be able to verify that it was from Alice. So the first step is that Alice computes the signature. Let's call this signature S. And actually, even this signature is secret. And how is this calculated? So this is just the signature of Alice on the message M. And the signature is using the private key for signing, so using D2. Okay. And last time we said that we don't sign on the message itself, we actually sign on the hash of the message. So actually, this is what Alice computes. Now, she wants to send S and M, both of them, to Bob, but she wants to send them in an encrypted manner. So step 2 is that, again, Alice encrypts it. So Alice encrypts SM to obtain the text that she's actually going to send. So I don't know, let's call that one X. And this is going to be public because this is what Alice is going to send to Bob. And this is just going to be an encryption of S and M. But this has to be encrypted in a way that Bob can decrypt it. So we encrypt it using E3, using Bob's public key. Okay, so this is the result of encryption using E3 of SM. Okay, and Alice sends this to Bob. So the message that is going through here is just X. But if I want to really expand it, it's the encryption. Okay, let me write it entirely. This is the encryption using E3 of the signature using D2 of the hash of the message and the message itself. This is actually what Alice is sending, but we called all of that X. Okay, now Bob wants to decrypt and wants to make sure that the message is actually from Alice. So Bob has X now, but we know that Eve and Charlie have X as well. That's not a big deal because only Bob can decrypt X. So Bob decrypts X. Okay. X. Actually, this one was supposed to be the same color. Okay. So if Bob decrypts X, what does he get? So he's decrypting. First of all, in order to get X in the first place, I encrypted using E3. So I can just use the corresponding secret key to decrypt. So Bob uses D3 to decrypt. So decrypt using D3 of X. And this is, again, by definition, as we said before, since X was the encryption of SM, the decryption of X is just SM. So now we are in this situation where Alice used to know S and M, and she encrypted all of them and sent them over. Now Bob could decrypt, so Bob knows S and M as well. Yes. Sorry. Okay. Yeah. So this is basically the encryption of both S and M. And so Bob can decrypt and he gets both S and M. But these are still secrets. So Eve and Charlie don't know either S or M. Okay. But now the next step is Bob has the message. He wants to make sure that it really came from Alice. So Bob has to verify Alice's signature. So this is our last step. Bob verifies Alice's signature. Now, how was this done? Well, you just check if you run your verification function on S, does it really give you M or not? So S is the signature. If I run the verification function on S, I should get my message back. Basically, I can say by checking whether this happens, whether verifying S, and by the way, in order to do verification, so S was a signature using D2 here. So in order to verify, Bob needs E2, but that's fine because all of our E keys are basically public keys, so Bob knows E2. So verifies it using E2 to see if this is equal to M. And if it is equal to M, then Bob knows that Alice really signed M and not a different message. So the message has not changed. Okay. Oh, yes, hash of M. I constantly forget about the hashing, yes. So we signed the hash. So you have to verify that this is equal to the hash of M. You're right. Okay. So basically what's happening here is that when Alice wants to send a message to Bob, what are the keys that are being used? I'm using Alice's signature keys because in order to sign, Alice needs to use her own secret key for signatures. And then in order to verify that signature, Bob needs to know the corresponding public key. But I'm using Bob's encryption keys. So I'm using Bob's public encryption key to encrypt and Bob's private encryption key to decrypt. Now, the opposite is just like the mirror image of this. So if Bob wants to send a message to Alice, it would be very similar. The only difference is that we're using different keys. So now we will use Bob's signature keys to do the signing, and then we will use Alice's encryption keys for the encryption and decryption. So if I just want to add it here, if Bob wants to send a message to Alice, let's say Bob wants to send some message M prime to Alice, what does he do? He first signs it. So sign the message, well, sign its hash, but he can sign using D4. So sign using D4, the hash of M prime, and take M prime itself as well. Take all of this and encrypt it to send it to Alice. But when you encrypt, you have to encrypt using E1. Okay, so now both parties can communicate with each other, and whenever you receive a message, you can be sure that no one else read the message, and you can also be sure that no one else changed the message. So we have secure communication, secure and authenticated communication. Okay, but now let's finally get to the main topic of this course, and let's try to create a cryptocurrency. So everything we said until this point was how do you send messages? How do you make sure a message came from a particular person? How do you make sure something is not changed? How do I actually create a currency using this? Well, the first point I have to fix in my currency is how I really have accounts and identities and things like that. So if you have, for example, a bank account is a very well-defined thing. But what I want in my cryptocurrency is some sort of anonymity. So I don't want your money to be connected to your real world identity. So instead of saying that I have some centralized place where you can go and create accounts, I say anyone can create their own accounts. Okay? But the accounts that are being created, I need to pick something that anyone can generate. So I know how to generate keys. I'm just going to say, if you want to create a new account, just generate a bunch of keys. Okay? And so you generate keys, and your public key, your public signing key becomes your identity, and your private signing key is what you keep to yourself to control your account. Okay? So that's the main idea. So creating an account is just generating keys. And you don't have to even announce them to anyone. You can just create an account on your own. We've seen how to do this with RSA. You can also do it with any other crypto system. But that's it. All I need is that I need to generate two keys. I need to generate a public key E and a private key D. This is how I create an account. And then I say E is basically my public identity. So in my cryptocurrency, I will never use a real world name. I will just use this name E. That's how anyone else can refer to my account. And then D is basically used for signatures. So D is my private key, and I can use this for signatures. Okay, that's equal, I don't know where that came from. Okay, yeah, so D is used for signatures. So suppose that I have some money, let's say I have 100 Hong Kong dollars. What everyone in the network is supposed to know is that someone with the private key E has 100 Hong Kong dollars. They don't know who this person actually is. They just know that someone with this, with this public key E has this much money. And now if I want to transfer this money to someone else, I have to provide a signature. But only the person who has the corresponding secret key D can provide the signature. But everyone else can verify my signature. So I have a situation where I don't really need to have a name. I can just have my public key and my private key. And since signatures can only be created using my private key, everyone else can verify that the owner of this account is making some transactions, even though they don't know who the owner is. Okay? That's the first idea that we have when we want to create a cryptocurrency from scratch. Now, the second idea is basically this idea of transactions. How do transactions even work? So what should a transaction be? Generally, I want to say that I'm sending some money, right? So I have to say that I have a bunch of coins. It can be Bitcoin or any other currency that I'm using here. And I have to provide a bunch of information. I have to say, first of all, what's my identity? And by identity, I mean my public key. So I have to say, I'm a person with this particular public key, and I have these many coins, and I want to send them to a different person with this other public key. Okay, so what is the required information here? We need the identity of the person who's actually sending the transaction, right? So let's call it sender. I need sender's identity. And by identity, again, I always mean public key. Whenever I say identity, I just mean public key. Now, to be very specific again, I always forget hashing. In Bitcoin and Ethereum and so on, your public key is not really your identity. Sometimes the hash of your public key is your identity, but I don't care about that at this point. So let's just say that in order to create a transaction should contain the sender's identity or public key. It should, of course, contain the recipient's identity. And this is also the recipient's public key. It should have an amount, right? So how much do I want to send? But what else do I need? Well, I need to prove that I have the money that I'm trying to send, right? So I somehow need a proof of ownership. Again, if we think about normal bank accounts, if your account is empty, you cannot send anything, right? Or if the amount is more than your balance, you cannot send it. But what else do I need? I also need a proof of consent. Meaning that I have to somehow be sure that the transaction that I'm seeing was actually created by the sender, because maybe someone else is just trying to use the sender's money. Okay, so I need to somehow create a concept of transaction that has all of this information in it. Now, we've already established how we can have identities. We said we just use public keys and each person can just generate their own identity, right? And actually, there is no limit on how many keys you can generate. So if you like to use many different accounts, you just generate as many keys as you like on your own machine. So I don't have a problem with these identities. And honestly, if I want to send money to you, I know my own identity and I just ask you, what's your public key? You tell me your public key, I send money to that public key. So these things are easy. And of course, the amount is also quite easy. Like I know how much I want to pay. Now, let's jump over proof of ownership and let's go to proof of consent. So how do I prove that I'm actually the owner of the funds that I'm trying to send? Well, we have the sender's identity or the owner's identity here. So this is the public key of the owner of these coins. So if I just have a signature from the same owner, I can be sure that the owner actually approved this transaction, right? So this is just a signature from the sender, the person who's sending the transaction. Okay, so the sender can create a signature because the sender is the only one who knows their own secret key. And in order to create a signature, you needed the secret key. So, and by the way, what is this signature on? This signature is going to be on the entire transaction. So the message that you sign is the hash of the entire transaction. Okay. So proof of consent is also done, not as easy as the rest, but doable. Now we get to the main problem here. How do I prove ownership? So I want to prove that I have 5 coins in order to be able to send you 5 coins, right? How do I prove that I ever received 5 coins in the first place? Well, I can just give you a pointer to the previous transaction where I received these coins, right? So if I want to prove that I have a bunch of coins, the best way to show it is to say, here's the transaction where I received this. So the proof of ownership is actually going to be a hash pointer because, of course, we're doing crypto, so we're using hash pointers. And this is going to be a hash pointer to the transaction in which I received this money, to the transaction that paid the sender. Okay, so this is how my transactions are going to look like. It's a bit early for this one yet, so let me put it down. Okay, so, but to just make things a little bit nicer, I might have a situation where I'm receiving money from many different places. So maybe I don't want to just have one hash pointer. Maybe I want to have many hash pointers to all the previous transactions where I got this money. And maybe I want to just use the same transaction to pay many different people. So I don't need to have just one recipient. I can have many recipients. Okay. So this is how my transaction is going to look like. And this is actually very close to Bitcoin now. So my transaction structure is like this. I'm going to have my transaction and basically my transaction is going to have a bunch of inputs. And the inputs are, the way you have to think about it, these are the monies that are flowing into this transaction. Okay, so I will have some inputs. And each input is basically a pointer to a previous transaction. So let's say if this is transaction, I don't know, 1000, maybe I have a pointer to transaction 3, I have a pointer to transaction 7, whatever. Okay. Each one of these pointers is telling me where I got the money that I'm spending in this transaction. So hopefully, if someone goes and checks transaction number 3, they will see that there was an output there that gave money to me. And then, of course, I used the word already, so I'm going to have a bunch of outputs. And the outputs are basically going to say how much money is paid to whom. Okay? So every input is a pointer to a previous transaction. And every output just has an amount and a recipient. Okay, but I kind of like, so every input shouldn't be just a pointer to a previous transaction. It should be a pointer to a previous transaction's output. Because maybe the previous transaction, maybe transaction number 7 was paying 1,000 different people, and I'm saying I'm person number 4 in transaction 3, and I've been paid this much in that transaction. I'm now using those coins here. So every input is a pointer to a previous transaction's output. So maybe I say transaction 3, output number 7. Transaction 7, output number 9. So what I'm saying here is that I'm saying if you look at the previous transactions, if you look at transaction 3, you will see that I was paid some money at index 7 of that transaction. So I was the 7th payee of that transaction. Okay. And I'm saying I'm using all the money that I was paid in that transaction to now pay someone else here in this new transaction that I'm creating. And of course, this new transaction is definitely going to include my identity. So this is, it will have the sender. So if I create a transaction like this and I give it to you and you have the history of all the transactions that have happened until now, you know who I am as the sender. So you can just go back in the list of transactions. You can look at transaction number 3 and look at output number 7 of that transaction. And you can check if that output was really paying me. And if it was paying me, then I have the right to use those funds now. Okay. So this transaction has its sender information. It has a bunch of inputs, which are pointers to outputs of previous transactions, and everyone can check these, assuming that everyone knows the list of all transactions that happened in the past. Okay, and then, of course, it has outputs, which basically says, maybe from this transaction, I don't know, I got 2 Bitcoins. Maybe I was paid 2 Bitcoins here, and here maybe I was paid 5 Bitcoins. So now I have 7 Bitcoins and I want to somehow allocate that. And maybe I say, give 1 Bitcoin. So in the outputs, I say 1 Bitcoin should go to this particular identity. Let me change my color again. So maybe I say send 1 Bitcoin to E1. And again, I'm using public keys as identity. So I'm saying send 1 Bitcoin to the person whose public key is E1. And I'm saying maybe send 4 Bitcoins to E2. So now I've spent 5 Bitcoins out of the 7. And maybe I say actually send the other 2 Bitcoins back to myself. Right? I can do that too. I can have a transaction that pays myself. And this is useful because maybe I had an output here, which was large. So let's say I've been paid 5 Bitcoins at some point, and I want to pay someone else a much smaller amount. So I can just pay that smaller amount to them, and then I can create another output that repays the rest of the money to me. Okay. And of course, the entire thing, so you need a signature, and this should be a signature on the entire thing. on this whole thing, I need a signature. Right? And the signature should be by the sender. Okay. Now, how do you verify? Again, it's too early for double spending. I'm really excited to talk about double spending today. Yeah. So how do you verify a transaction? How do you verify that the transaction is correct? So verifying a transaction. Now, I have to first tell you the assumption that I'm making here. And the assumption is that everyone knows what the previous transactions were. And this is a huge assumption. We will get back to it. But for now, let's just say that you are someone who knows all the previous transactions and you're seeing a new transaction. How can you verify that this is a valid transaction? So when is a transaction valid? Well, you have to first verify that the sender, the person who's created this transaction, actually signed it correctly, right? So you need to verify the signature. Okay, so that's the first thing. Verify the signature. And the reason we do this is to make sure that the transaction is really from the person that it's claiming to be from. To make sure the transaction is approved by the sender. Okay, then you verify that the sender actually owned all the monies that he's claiming. So if I have a sender, and again, just in this example, the sender is saying, I have some money at transaction 3 output 7. You have to go back to transaction 3 output 7 and see that that money was actually paid to the same identity. Okay, so check identities of all inputs, basically. For every input in this transaction, I have to check that it has the right identity. Okay, I don't check the identities of the outputs. That's not my problem. If the sender is somehow sending money to an account that does not exist, they're lost. The money is gone forever, right? But as someone who's just checking the system to see if a transaction is valid or not, I don't care about that. So actually, this is a problem that we have in Bitcoin as well. You can send money to addresses that don't exist and don't belong to anyone, and that's the best way of burning money. But yeah, so for now, I don't have to do any kind of check on the outputs. I just need to make sure that any money that is being spent actually belongs to the person who's creating this transaction. That's all I care about. I don't care if they burn their own money. Okay. Now I have this. What else should I check? Well, this is actually a very simple check, but a lot of people forget this. I have to check that the sum of all the inputs is greater than or equal to the sum of all the outputs. Right? So the amount of money that is flowing into this transaction should be greater than or equal to the amount of money that is going out. In other words, the person who's sending the transaction should not be able to just create new money out of thin air. That's not acceptable, right? But again, notice that I don't say it should be equal. I say it should be greater than or equal. I don't care if you burn your own money, okay? So you can have a situation where you get like 7 Bitcoins in, and then you only transfer 5 of them. If you do that, you've burnt the other 2 Bitcoins. Okay, just don't do that. So these are the things that I have to check. Now, do I have all of these things? Well, I have the sender's identity. Of course, it was written here. I have the identity of all the recipients, because every output basically has the identity of one recipient. So I have these things. I have the amounts. Of course, the amounts, again, I have several recipients and several amounts. So that's fine. I have the proof of ownership because I have a signature on the entire thing. And again, it's very important. It's not enough to have a signature on just one output, right? Because if you have a signature on just one output, maybe the sender did not approve the second output, right? And it's not enough to have separate signatures on each one of the outputs because maybe the sender was creating different transactions and didn't want to do all of them at the same time. So you really need a signature on the entire thing. A signature that says exactly this transaction that you're seeing with all of its details, everything is approved by this sender. Okay? So that's the proof of consent. And then we said for proof of ownership, the sender just gives me a pointer to the previous transaction. Right? And if I know the previous transactions, I can just check. I can see that the sender actually received that money. But now, finally, we get to my favorite problem, which is double spending. This system is quite great in everything, except that suppose I have a transaction at some point. Let's say at some point, I have, let's say, transaction 5. And in this transaction, there was an output that is paying 5 Bitcoins to Alice. Okay. So now I know that Alice has 5 Bitcoins. So later on, Alice can create another transaction. Let's just call it transaction 100. And this is a transaction created by Alice. And she takes these 5 Bitcoins. So she puts a pointer to this transaction and says, at this particular index, I received 5 Bitcoins. And she says that I want to send these 5 Bitcoins to Bob. That's fine. She has 5 Bitcoins. She can send it to Bob. But then let's say that at the same time, or maybe a little bit before or after that, Alice creates another transaction. And she refers to the same money. So she gives a pointer to the same money and says, I want to use these 5 Bitcoins and I want to pay these 5 Bitcoins to Carol. And again, I write Alice, Bob, and Carol and so on. You know that these are actually public keys. They're not real names. We never use names. Okay. So we have a problem here. Alice received the 5 Bitcoins only once, so she cannot spend it more than once. She cannot do what we call double spending. So I have to add an extra rule that says every output of a transaction can be spent at most once. So if you've already spent this output that paid some money to you as an input here, then you cannot spend it again as an input in another transaction. So this is the last condition that I have to add when I verify a transaction. I have to say every output can be spent at most once. Again, I'm very careful with my words here. I don't say it has to be spent. I say at most once. Again, if you have some money, you don't want to spend it, it's none of my business. So generally, the system allows you to lose your money. You have to be careful about what you do. Okay. So this is now how I can verify a transaction and make sure that everything in this transaction is working correctly. But now this last check is actually very different from the previous checks. Because for all of these previous checks, I could kind of do the check on this transaction itself. So for example, when I wanted to check a signature, I could just say, okay, I have the transaction, I take its hash, I verify if the signature is on the hash of this transaction, I'm happy, right? So this was a very local thing. When I want to check that the sum of inputs is more than or equal to the sum of outputs, I just have to do a bunch of sums, right? These are easy calculations to do. Now, even this one is easy because for every input, I have a pointer to the output that paid that money. And I can just go to that transaction and see if that transaction really paid the money to this particular sender or paid it to someone else, okay? Or maybe that transaction doesn't even exist. In all of these cases, this would be an invalid transaction. But the problem with this last one is that it's a much harder thing to do. I have to basically go over all the transactions that I have in my system, right? Not just the transactions that were referenced here. And I have to see if there is any transaction that has previously used one of these same inputs that I'm using here. Because I have to make sure that every output can be spent at most once. So for this last check, I have to actually have a list of all the transactions. So I wasn't very clear about how this system works. I was just telling you there is someone who's creating an account, like a bunch of people who are creating accounts like this. And then we have a bunch of transactions. And I was just saying, what happens if you want to verify that the transaction is correct? But I didn't really say who gets to do the verification. I just said how to do it. So now we have this problem here. Who gets to verify the transactions? Now, a very simple idea can be to say that, okay, I just use something like a gossip protocol. So I have a network. We are all connected to each other somehow. And whenever I want to make a transaction, I just announce this transaction on the network. So I just tell one of my neighbors on the network, hey, I have this transaction. And then that neighbor sends the transaction to all of its own neighbors. And then everyone just sends it around like a gossip until everyone hears it, right? Because ideally, I don't want to have any kind of central authority. I want everyone to be equal. That was lecture 1. So, okay, if we do that, we can be sure that with certain nice assumptions, assuming that the internet works, we can be sure that everyone hears about all of the transactions, right? So if I make a transaction like this, and I just announce it on the network, and then everyone tells their neighbors, everyone will eventually hear about it, and hopefully our internet speed is great. We don't have too much latency. Hopefully after 5 minutes, everyone knows about the transaction, right? And then I can say everyone knows about all the transactions that happened in the past. So everyone has the history of all the transactions. So everyone on the network can do all of these checks and we can be happy. But unfortunately, that's not really how this works. So generally, if you have an easy solution in this course, it's a wrong solution. Now, I want you to see what happens here. So let's say I have 2 transactions like this. And let me just give them new names. So I'm going to call this one TX1, and I'm going to call this one TX2. So let's say that Alice had received 5 Bitcoins before, and she's a cheater. She's now creating 2 different transactions and trying to spend the coin at the same time. But now here's what she does. She says, I know how the system works. I know that whenever I announce a transaction, this transaction will just go through the gossip protocol. So let's say we have a network. Let's say this is Alice. And we have some sort of connectivity in this network. So Alice is connected to a bunch of people. They are also connected. I don't know. I'm not very good at drawing. Okay. So let's say I have something like this. And what Alice does is that she also creates a connection to somewhere in the network which is really far away. So let's say Alice is in Hong Kong. She creates a connection to somewhere, let's say in the US, on the other side of the network. And then she announces both of these transactions at almost the same time, or at exactly the same time. Let me just add a bunch of notes here. I want to make these paths a bit longer. Okay. So here's what she does. She says, transaction 1, she announces it here. And then she announces transaction 2 here. Okay. Now this node has heard about transaction 1, but it has not heard about transaction 2. So from this node's point of view, transaction 1 is a valid transaction because this node checks transaction 1 against all of the previous transactions and sees that there is no double spending. Okay, and I'm assuming that everything else was okay with this transaction. Now, similarly, from this node's point of view, transaction 2 is the valid transaction. Now, let's see what happens when we continue this. So each node tells its neighbors about the transaction. So this node tells this node about transaction 1. This node tells these two about transaction 2. And then this just continues. And they don't even have the same speed. So it might be that transaction 1 goes a little bit faster and gets propagated to everywhere here, whereas transaction 2 is not propagated that much. Okay. So at some point, there's going to be a node, for example, this node, that has already heard about transaction 1. And now it's hearing about transaction 2 for the first time. Now, what happens from this node's point of view? From this node's point of view, transaction 1 was a valid transaction. So now when I'm hearing transaction 2 that is double spending the same money, I just say transaction 2 is invalid, right? So I just ignore transaction 2 and I don't send it to my neighbors either because it's an invalid transaction. I don't want to just propagate invalid transactions. But now there is another node, let's say this one here, who has heard transaction 2 first, right? So from this node's point of view, 2 is the correct transaction. 2 is the valid one. And then at some point, it also hears transaction 1, maybe from one of its neighbors. But then the exact opposite thing happens. So this node, it has already agreed that transaction 2 is valid. So when it sees transaction 1, it thinks that transaction 1 is double spending and invalid. So basically, and let's say all of these people also hear transaction 1 first. My network is now divided in 2 different camps. There are people who believe in transaction 2, and there are people who believe in transaction 1. But so what happens when we have a division like this? People who believe in transaction 1 believe that Bob now has the 5 Bitcoins. So from their point of view, Bob can spend 5 Bitcoins. Whereas from the other side's point of view, Carol can spend those 5 Bitcoins. So basically, we have a complete separation in our monetary systems. We have 2 different camps, and each one of them is working with a completely different history from now on. And then now, if Bob makes a transaction using these 5 Bitcoins, the people in camp 1 are going to accept that transaction. The people in camp 2 are going to say, you never had this money in the first place, so this is an invalid transaction. Okay, and this was just by 1 double spending. So every time you double spend, you can create a division. And so yeah, this money doesn't work. Okay, unfortunately, we ran out of time for today. So I told you the problem with double spending. In the next session, I'm going to talk about solutions and how to make sure we don't have double spending. And basically, the solution is that we have to reach some sort of a consensus. We have to reach a situation where everyone agrees about the history. Everyone agrees which history is the correct one, right? And well, the easiest way to reach a consensus is to have some centralized authority, to have a central bank. If I have a central bank that tells me this is the history, and I always just trust the central bank, then everyone has the same history. And that's actually one of the topics we will talk about, which is like what people call central bank digital currencies. You've probably heard that there's going to be an electronic version of the Hong Kong dollar. This is what it is. It's not really a blockchain. We will then talk about how blockchains work and how we can have a decentralized solution. Okay, I'll see you next week.